Not air.
It's not air? Right.
Well, the target could be air.
It could be air, but you know, the mu sub 0 is permeability in actually vacuum. So what's bizarre is as I move through here, you're going to be able to see that we can not only tell the difference between air, but different elements. For instance, presence of hydrogen, oxygen, or other gases will induce a difference effect in the sensor. Here, we image ceramic, Delrin, low density polyethylene PEEK, and graphite composite. You'll notice that some of these curves go down while the other curve goes up. That was quite interesting. Why would it do that? But you can also see that we can tell the difference between those plastics or those non-conductors. Here we zoom in a little bit. This is that resonant frequency shift that you saw earlier where we see the resonant peak. That's air, that's Delrin, that's low density polyethylene. And on that voltage scale, it's a pretty big change. You can spot the difference, yes?
So on the graph on the left side, you are taking your scanner and you're scanning across a material?
What we do is we park the sensor in intimate contact with
You're moving one in relation to the other?
Right,
okay.
And then we back away from it. And the reason...
How fast are you moving it?
How fast?
Yeah, does the angle of these curves change based on how fast you're moving?
No.
Is there a time effect is what I'm asking?
There's no time effect other than the time effect you induce by way of either parasitic capacitance or induced capacitance by way of tuning. Every time you put in capacitance, it has a time constant. So the quicker response you want, the lower you want the capacitance to be. I always tune with the minimum amount of capacitance and try to wind it to as close to the frequency that I'm looking for.
So if you were to scan at a different rate,
now, you're talking surface speed or moving away speed?
Surface speed.
Okay.
If you were to scan at a different surface speed, would you achieve those exact same plots, or would they be slightly different?
I did a number of tests where we're scanning over a crack at dramatically different speeds, and other than affecting data acquisition, we get the same result. In other words, the output peak is the same. And the thing you have to be careful of is maintaining the same data density, because if it's a small phenomenon, you'd better be acquiring data very fast if you're going to move fast. That's the only caveat to that. Yeah. Yes?
Did you see any effect on sample sizes? For example, sample is oval shaped or circular or rectangular. Do you see difference in your output? Sample geometries.
Yes. If the geometry of the target changes in shape,
yeah.
does that affect the output?
Right.
No, because we can scan a circumferential object, scan around it, or we can scan a flat plate, or we can scan a surface that has varying geometry and still get the same sort of output. So it's not subject to output unless those geometries affected your distance. Because if distance increases, your resolution goes down some. But the physical shape of the part doesn't affect the signal output.
Yeah, so that means that result is somewhat insensitive to the thickness of the sample signal.
We have a range limitation depending on how you build the sensor. And everybody knows about the range limitations when you're dealing with eddy current, because eddy current, as you increase the conductivity of the target, eddy current is diminished because it's being pulled into the eddy currents. Yes?
If you don't have boundary conditions, why do you have a change in slope?
Oh, because I'm moving away from the target. That was a technique that I developed some years back. I found that if I had a target of unknown material or known material, put the sensor in front of it, and moved away from the target, you get a characteristic slope here. And at about 0.66% of reaching the maximum, I call that our depth of penetration. I'm able to relate moving away from the target in air to depth of penetration. Does that make sense to you?
You're moving across it and you're
Away
moving
from it.
away at the same time?
No, I'm not moving across it, I'm moving only away from it, to determine how far into the object I can scan. I'm sorry, yes?
What is the sensor diameter, or what's the ratio between sensor diameter and distance to target?
In this particular sensor, it was 80 thousandths outside diameter, 0.080 inches.
2 millimeters.
Yes, at 35 thousandths is a mil, yeah, about, just slightly over 2 millimeters, yeah. I've got some images of scans of plastic with different plastics in it and air, and those are great images to show the effect here. But I wanted to touch a little bit on this permeability effect. You can see that permeability of steel, aluminum, Teflon, nickel, and vacuum are listed here. But you can see here, permeability of these four materials are very close to one another. So in using permeability alone, you cannot really discern the difference between these materials, yet we do. And that put me on to this other, I guess, variable called susceptibility. Susceptibility is relative permeability. In other words, you have the permeability of the target divided by permeability of free air, or excuse me, of a vacuum, -1. And what that does is it takes the very subtle differences in permeability and amplifies it, yielding this chart over here. Now all of a sudden, everything begins to separate. You can tell the difference between aluminum, ammonia, bismuth, copper. And this is correct. We can tell the differences between these things. We can tell the differences between ceramic and plastic and air and all of these things. But it makes sense, and it makes sense because the permeability of steel versus the permeability of Teflon, when you look at it in terms of susceptibility, is about a 700 to 1 relationship. In other words, the permeability of steel is 700 times greater than that of Teflon. And if we can resolve permeability down to that very low level by way of our high Q, because we get very high amplification, if you remember, we get narrow bandwidth, so it acts as a natural filter. It gates out noise, and then we have a clever amplification circuit that we put to amplify the signal out. But the sensor itself produces an inherently noise-free output because of all of this tuning that we do. And because of that, we can discern a 700 to 1 difference in permeability. Does that make sense? Going from permeability to susceptibility as to why we can see these differences? All right, this is the boring part. This is paramagnetic versus diamagnetic. If you remember the slope of those curves, some were positive, some were negative. And I believe the reason is when you look at magnetic susceptibility, you have a thing called paramagnetic materials, diamagnetic materials. You have ferromagnetic materials and anti-ferromagnetic materials, but I'm going to talk about these two here. In paramagnetic, you actually have electrons in the outer shell where you have an odd number basically, or you have unpaired electrons. And that induces a magnetic field such that when you put a magnet in front of it, it has a slight attraction because you have an unpaired electron making a magnetic field which has not been canceled out by another electron being pulled to the magnet. Our sensor acts as a magnet. It's an oscillating magnet. And now here in diamagnetic materials, you have paired electrons. They cancel out the magnetic field, so now you have a slight repelling effect. And that's basically where you get susceptibility. That is the susceptibility number. They are equal. And if you remember the positive versus the negative curve, it tends to separate out the paramagnetic and diamagnetic materials by way of that curve. Here, this caused me more trouble really than anything else. I didn't understand why we could detect paper inside of graphite composite, FOD, Teflon. And I was doing that for Northrop Grumman, an experimentation for them. where we were detecting Teflon discs and paper FOD that is from the backing of composite. And the question was, well, that's fine, you can see it, why? We're not interested in a magic box. And so I made a black Delrin block, pressed into it low density polyethylene plugs, and then scanned it on its face, right here. And you can see here we very clearly tell the difference between one plastic and another. So two different insulators being discriminated very, very readily. Here is just two blind holes, flat bottom holes, one a 32nd from breaking through to the other side, the other one a 16th of an inch from breaking through to the other side. But we scan the other side here. So now what we're doing is we're measuring the difference between wall thickness of an insulator with the background of air. Good.
When they asked why,
Yeah.
what did you tell them?
I didn't know. I didn't know. It just did. And this was very, very early on in my research. They handed me the sample. Can you see this? I scanned it. Yes, I can. I'm not an eddy current expert. I know a lot about eddy current now, but in those days, I was just developing my sensor without having a thorough background in eddy current. And many of you probably know more about eddy current than I know. I've certainly become an expert in this and appreciate the difference between eddy current and this now. But it took a while for me to explain. I had to do some digging on that and a lot of testing.
Now this graph, you built, basically made a raster scanner where you just moved
That's
the
it,
sensor.
yeah. We have a number of different types of motion control systems. One is I have a test setup where you can basically throw anything you want to in it because, you know, I'm in a meeting, the first thing I get asked is, can you image this or can you image that? And I end up going home with a bunch of samples. And so I needed a scanner that I could just throw parts into and scan it. That's a raster scanner. We have the sensor, it's spring loaded, we go across.
How fast is it moving? Like, how fast would it take to make this pixelized scan?
A minute.
And how big is the part?
That part is probably 6 inches by 4 inches. We can go faster, but I have stepper motors on this system. That's as fast as they would carry it. It seems to be able to scan at very, very high speed. And you know, if you've ever seen one of these OS systems that Northrop has, where they're shooting a column of water at a target, very big composite samples, it'll be in there for hours without getting scanned. This could scan much faster.